Our team chose to take on the idea of collecting unharvested albedo radiation and turn it into a practical field-ready design. Flexible solar cells are at the forefront of semiconductor research. With advancements in this cutting-edge technology occurring every day, we chose to merge these two renewable energy sources together. By using this emerging technology of flexible solar cells, they can be more easily integrated with the smooth, round features of modern wind turbine blades. Moreover, by utilizing solar energy generation from albedo radiation, we can ensure that the panels collect the sunlight even when they're not directly facing the sun. In turn, we can merge this new idea with existing renewable power generation infrastructure, and both efficiency and cost effectiveness of the renewable energy sources have the possibility of increasing. Our team's idea was that by adding solar cells onto the surface of the turbine blades, overall efficiency of the turbine could increase. The nominal power that is generated from the solar cells from the albedo radiation and direct sunlight could be used to power the wind turbine's control systems, primarily the yaw and pitch control systems. This would reduce the need for power transformers and lines used for the controls and communications. Our team created a mock-up of a wind turbine with rigid solar cells integrated into the blades to show the possibilities of harvesting the unused albedo radiation. We then modeled different types of ground beneath the wind turbines to show the differences in the intensity of the albedo radiation.
I'm here to explain how we simulated the different surfaces. We used brown to simulate dirt, black to simulate asphalt, white to simulate snow, blue to simulate ocean, and gray to simulate a rocky or dark surface.
For our data collection acquisition process, because all of our data collection was at night, we used a shop light to simulate the sun. This shop light was placed a meter away from the center of the turbine and at the top of the topmost blade. What we also did was we angled it down at a 45-degree angle to give us the maximum amount of albedo radiation reflection. This way there would be a lot of reflection off the ground to guarantee us strong data about albedo reflection as well as direct solar radiance from the shop light. This is our wind turbine. As you can see, there are 6 solar cells on the 3 blades with 2 cells per each blade. Each of the cells' voltage reading is read through the ESP32 on the middle of the wind turbine. To prevent the need for a slip ring or a way to get the data off, we have the ESP32 and the power on board the turbine, we'll use Bluetooth to talk to another ESP32, which does all of our data acquisition. As you can see, when I press this button, the turbine spins, which simulates the turbine. The red LED, as we change the colors on it, simulates the different yaw and pitch values of the turbine that these solar cells can be used to.
So after we get the data from the ESP on board, it's going to send Bluetooth to this guy, and this guy's going to do all the data logging and analysis. So if we come over here, this is the MATLAB UI that we made from the ground up. Here I can select the proper COM port. This one's going to connect to the ESP that is not on the windmill. So then if I go over to the data tab, I can see all the data being populated here. So as James spins the turbine, I have the data record here, but then I can go over to plot and I can pick any one of these, and if I plot it, click update, I should see a nice little sine wave right there. This is how we did our data acquisition. Once we're done, we can go ahead and come back over here. We can click quit. We can type in whatever we want our Excel file name to. We can click export, and that'll be our data. So here we have a little app that helps us see the data a little bit better, a little bit quicker. So if you see on here, we have every single solar panel as well as their voltage values. Right now, they're pretty low because we don't have the shop light on. So once we switch that guy on, you'll see that all the voltage values seem to spike pretty well. And this app also connects straight to this Google Sheet. So we'll have a QR code up where you can monitor this at your own house, at your own home. And then again, we can control yaw and pitch just from the app. And that changes the LED on the